On the corner of King Street and Pitt Street in central Sydney, thousands of pedestrians step across a set of cast iron stormwater grates every hour. They see asphalt, stone paving, heritage sandstone facades, and the constant traffic of city buses. There is no sound of rushing water, no visible slope, and no sign of a natural channel on any modern street directory. Beneath that pavement, 4 meters below the traffic, 6 million litres of fresh water surge through a hand-carved sandstone and brick tunnel every single day. What is remarkable is not that a river runs under the financial heart of Australia's largest city, but that for more than a century, civil engineers and urban planners treated its presence as a minor drainage inconvenience rather than a permanent geological feature. How many hidden waterways across the continent are quietly dictating what can be built, mined, or inhabited above them? Before this investigation reaches its end, it will examine a river in the Kimberley that carves straight through a 350-million-year-old fossilized reef, and a subterranean torrent in the Tasmanian highlands that plunges into a vertical limestone sinkhole 300 meters deep. For generations, the conventional understanding of Australian geography rested on a straightforward premise. This is the driest inhabited continent on Earth, defined by low relief, ancient eroded soils, and surface catchments that either evaporate in the interior or run directly to the sea. That conclusion was entirely reasonable when early colonial surveyors mapped the coastline and interior using surface triangulation, barometers, and visible river channels. They drew boundary lines along watersheds they could see, assuming that what lay beneath the topsoil was solid, static geology. That assumption broke when civil excavations and hydrogeological surveys began encountering massive subterranean discharges that bore no relationship to surface topography. Across every state and territory, rivers have been entombed beneath urban concrete grids, swallowed by vast karst formations, or diverted into ancient buried bedrock valleys. In New South Wales, the confrontation between urban development and hidden hydrology began in 1788 at Sydney Cove. The Gadigal people of the Eora Nation had long understood the seasonal flow of the freshwater stream entering the harbour, but colonial settlers quickly enclosed and polluted it. By the mid-19th century, city authorities buried the tank stream inside vaulted brick and ashlar sandstone culverts beneath George and Pitt Streets. Today, the tank stream remains a living drainage system, discharging an average of 6 to 8 million litres of groundwater daily into Sydney Harbour. Yet urban concrete is only one way New South Wales conceals its water. 200 kilometres to the southwest, in Kosciuszko National Park, Cave Creek demonstrates how nature accomplishes the same erasure. Flowing across the Coolman Plains, Cave Creek hits a belt of Silurian limestone and vanishes entirely into a dark subterranean gorge. It travels over 2 kilometres through unexplored cavern networks before bursting back into daylight at the Blue Waterholes. Further south in Victoria, Melbourne's central business district rests directly on top of a suppressed river system. Williams Creek originally carved a deep natural valley through the turf from Carlton down to the Yarra River. During the 1850s gold rush, rapid urban growth forced engineers to enclose the creek within a massive brick barrel drain beneath Elizabeth Street, measuring over 3 meters in diameter. Because the natural catchment covers more than 300 hectares of urban slopes, Williams Creek periodically asserts its original path. Major storm events in 1972 and 2010 surcharged the subterranean culverts, transforming Elizabeth Street back into a raging surface river meters deep within minutes. In eastern Victoria's Gippsland region, the same subterranean dynamics occur without human intervention. The Buchan River system feeds subterranean flows through Devonian limestone, where tributaries like the subterranean stream in Royal Cave carve kilometres of dark passages, maintaining a constant water temperature of 14 degrees Celsius while nourishing unique stygofauna adapted to complete darkness. To understand why Australian rivers vanish, one must trace the deep history of a continent that has remained tectonically quiescent for hundreds of millions of years. Unlike young mountain-building landmasses where high relief forces surface runoff into visible, steep-sided valleys, Australia's ancient crust has been subject to prolonged chemical weathering, planation, and carbonate deposition. In Queensland, this deep geological timeline created the subterranean drainage systems of the Barkly Tableland and the Cammerwheel Caves. During the Middle Cambrian period, approximately 500 million years ago, shallow inland seas covered large parts of northern Australia, depositing thick layers of marine limestone known as the Georgina Basin. As sea levels receded and tectonic forces gently uplifted the region, meteoric groundwater enriched with dissolved carbon dioxide began percolating through systemic joint networks in the rock. Over tens of millions of years, this acidic solution dissolved the limestone along structural fractures, carving out thousands of kilometers of subterranean conduits beneath an apparently featureless, dry grass plain. In the Kimberley region of Western Australia, on the traditional lands of the Bunuba people, a similar process played out on an even grander scale during the Devonian period, roughly 375 million years ago. An ancient barrier reef, constructed not by modern corals, but by extinct stromatoporoids and algae, accumulated along the margin of the Canning Basin. When the ocean retreated, this ancient reef structure was exposed to subaerial erosion, forming the Napier Range. River systems like Winjana Gorge and Tunnel Creek encountered this massive carbonate wall. Rather than cutting entirely through the ridge from above, Tunnel Creek exploited an existing network of subterranean solution cavities. The river carved a continuous 750-meter cavern directly through the limestone structure, running in total darkness beneath the limestone spine of the range before emerging on the opposite side. Dasyurid marsupials, roosting bats and freshwater crocodiles occupy the subterranean channel, utilizing a microclimate that has remained stable while the surface surrounding the range dried into arid savanna. South Australia presents a distinct geological mechanism for subterranean water transport, shaped by much younger marine transgressions and aridity. Beneath the Nullarbor Plain, a limestone karst block spanning 200,000 square kilometres across South Australia and Western Australia, the surface receives less than 200 millimetres of annual rainfall. Yet vast volumes of water move through the underlying tertiary limestone. Millions of years of mechanical and chemical weathering formed massive cave systems such as Cocklebiddy Cave and Cunalda Cave. Rain falling on the interior does not form surface streams. It drains instantly through thousands of blowholes and collapsed dolines, entering an aquifer that discharges directly into the Southern Ocean via high-pressure freshwater vents beneath the seafloor. Meanwhile, in the southeast of the state around Mount Gambier, Pleistocene limestone pitted with cenotes like the sinkhole at Umpherston intercept the regional water table, revealing clear groundwater moving silently toward the ocean just meters beneath urban suburbs. In Tasmania, where active glaciation repeatedly reshaped the landscape during the Quaternary period, subterranean hydrology cut through older, highly fractured Ordovician limestone. In the Mole Creek Karst National Park, over 300 mapped caves redirect major mountain streams into subterranean courses. Rivers such as the Mole Creek system plunge into sinkholes, flow for kilometers beneath forested ridges, and emerge at lower elevations as high-volume artesian springs. Geological Survey of Tasmania mapping demonstrates that these subterranean routes do not simply mirror surface valleys. They frequently cut straight under surface drainage divides, carrying water from one river basin into an entirely different catchment underground. But how do hydrogeologists prove where these dark, unmapped currents actually go when they disappear beneath hundreds of meters of solid rock? For over a century, official mapping agencies relied on surface elevation data and optical aerial photograph interpretation, methods that fundamentally failed to register subterranean hydraulics. The breakthrough in proving where these hidden rivers go came from a combination of geochemical sampling, airborne geophysics, and isotope hydrologic tracing. In the Northern Territory, researchers from CSIRO and the Northern Territory Geological Survey addressed the puzzle of the Daly River catchment using radon-222 isotope profiling and environmental tritium testing. While the surface river appears to drop to negligible flows during the dry season, in-stream chemical sensors revealed massive spikes in radon concentrations along specific stretches. Radon, a naturally occurring radioactive gas released when groundwater interacts with deep rock formations, decays rapidly with a half-life of less than 4 days. The presence of high radon counts in surface water proved that millions of litres of fresh groundwater were discharging directly into the riverbed from deep limestone conduits in the Tyndall limestone aquifer. In Western Australia, proving the geometry of ancient buried river valleys, known as paleochannels, required methods capable of looking through hundreds of metres of weathered regolith. In the Yilgarn Craton, traditional drill core programs executed by mining companies targeting nickel and gold inadvertently intersected deeply incised paleovalleys carved during the Mesozoic era. To map these features across thousands of square kilometres without drilling every 100 metres, Geoscience Australia and the Geological Survey of Western Australia deployed airborne electromagnetic surveys. By flying aircraft equipped with large transmitter loops at low altitudes over the desert, geophysicists measured the electrical conductivity of the subsurface. Because these ancient buried riverbeds hold brackish to saline groundwater contained within porous sand and gravels, they conduct electricity far better than the surrounding crystalline granite. The resulting inversion models turned flat, featureless Salt Lake country into clear, three-dimensional maps of ancient river networks hundreds of kilometers long, flowing beneath dry dust. A similar transformation occurred along the Murray River corridor in South Australia. Hydrogeologists using airborne laser scanning, or LiDAR, combined with electrical resistivity tomography, mapped thousands of paleochannel alignments invisible to the naked eye. LiDAR sensors mounted on aircraft pulse hundreds of thousands of laser beams per second toward the ground, measuring minute elevation differences of less than 5 centimeters. This sub-decimeter precision revealed subtle microtopographic sags on the floodplain, linear depressions where buried river channels are slowly settling under the weight of overlying muds. When researchers conducted electrical resistivity profiles across these LiDAR anomalies, the cross-sections confirmed active groundwater channels flowing beneath the dry floodplain. Further north in Queensland, seismic reflection profiling conducted for petroleum and coal seam gas exploration exposed the hidden extent of the Great Artesian Basin's recharge pathways. Seismic survey trucks driving along country roads lowered heavy vibrating plates onto the pavement, sending low-frequency acoustic energy down into the crust. Reflections returning from deep geological boundaries were recorded by arrays of geophones stretched along the roadside. The acoustic profile revealed structural faults slicing through impervious shale layers, creating natural vertical chimneys that force pressurized subterranean water upward into shallow sand aquifers and surface spring complexes. But as modern instrumentation brings these hidden water networks into sharp focus, a critical question emerges. What happens when human development, climate shifts, and resource extraction disrupt these ancient systems? The consequences of these hidden hydrological networks are not theoretical. They directly affect infrastructure integrity, agricultural viability, and urban planning across the continent. In urban Sydney, managing the continuous subterranean discharge of the tank stream and surrounding water tables costs municipal authorities and private developers millions of dollars annually. Deep civil construction projects, such as the Sydney Metro underground station excavations at Martin Place and Barangaroo, require complex tanking systems and continuous dewatering arrangements to prevent pressurized groundwater from flooding subterranean rail tunnels. When engineers cut into the Hawkesbury sandstone, they are not working in dry rock. They are intercepting fractures that have carried water from surrounding ridges toward the harbour for thousands of years. In rural agricultural zones, the unmapped depletion of subterranean flows presents an immediate threat to surface river ecosystems. Across the Great Artesian Basin, which underlies 1,700,000 square kilometres across Queensland, New South Wales, South Australia, and the Northern Territory, over a century of uncontrolled artesian bore discharge caused hydraulic pressures to drop significantly. The Bureau of Meteorology and Geoscience Australia recorded pressure declines of up to 100 metres in specific aquifers between 1890 and 2000. This pressure drop caused unique mound springs, natural discharge points that supported endemic fauna and served as vital water sources for traditional owners for tens of thousands of years, to dry up completely. State and federal governments initiated the Cap and Pipe the Bores scheme, investing over $300 million to replace open earth channels with closed piping networks, successfully recovering pressure in critical regional aquifers. The danger of ignoring subterranean hydrology becomes even clearer in Western Australia's Pilbara region. Massive open-cut iron ore mining operating beneath the natural water table requires continuous groundwater abstraction, pumping tens of gigalitres of water out of deep paleochannels every year. If these buried alluvial systems are overpumped, the water table drops below the root zones of native vegetation, leading to widespread mortality of stygofauna and fire-sensitive riparian trees like Melaleuca argentea. The Western Australian Department of Water and Environmental Regulation enforces strict monitoring regimes on mining operations, requiring re-injection of extracted water back into the aquifers to maintain regional hydraulic pressure. In the urban centres of South Australia and Victoria, hidden streams create significant geotechnical hazards. Dissolution of shallow limestone in Mount Gambier regularly forms sudden collapse sinkholes beneath roads, residential properties, and agricultural land, requiring ongoing monitoring by local councils using ground-penetrating radar. In central Melbourne, the enclosed brick culverts of Williams Creek require continuous structural maintenance by Melbourne Water to prevent catastrophic collapse under the heavy dynamic loads of modern tram networks and high-rise foundations. Yet despite advanced remote sensing and civil engineering, the vast majority of Australia's subterranean water paths remain incompletely mapped. What does the existence of these invisible, unmapped rivers tell us about how we draw our boundaries and understand the continent's future? In Western Australia, the most dramatic hidden river system on the continent sits beneath the arid surface of the Canning Basin. Beneath the desert sands, ancient paleo-valleys mapped by Geoscience Australia carry subsurface flows over hundreds of kilometres, discharging fresh and brackish groundwater directly into the Indian Ocean via offshore submarine springs beneath the seabed of the 80-mile beach region. Hydrogeologists estimate that these submerged discharge points vent millions of litres of groundwater daily into marine environments, creating localised freshwater plumes that support distinct marine ecosystems invisible from land. What kept these massive hydrological systems unnoticed for so long was not their depth or remoteness, but the legal definition of a river itself. For over 2 centuries, Australian water law and cartographic convention defined a watercourse exclusively by visible surface banks and open sky. Because surveyors mapped only what could be bounded on a 2-dimensional cadastral sheet, any flow that dipped beneath the topsoil ceased to exist in the official record. A significant portion of Australia's deep hydrology remains completely unresolved. Hydrogeologists from state surveys and CSIRO are currently attempting to map the exact subterranean velocity and volume of water moving through the deep fracture zones of the Great Artesian Basin, where groundwater ages exceed 1 million years. In many inland basins, intensive groundwater extraction is depleting these ancient reserves faster than scientists can determine where they recharge or which stygofauna communities depend on them for survival. The official maps hanging in planning offices and university lecture halls look complete, neatly bounded by blue lines and elevation contours. The ground beneath them is still largely unread. Which hidden waterway or unexpected geological feature in your own state or territory has always raised questions for you? Let us know in the comments below and consider subscribing to stay connected with our ongoing investigations into the continent's geography.